basically left our discussion till here. Purpose of making those small chunks of video is that it's easy to understand and easy to absorb too. Because if I would be giving you a lecture of whole presentation in a one video, you might skip it, right? Or you might say that we're so done with this. So this is the purpose of making small chunks and covering each and every topic. Okay, so now we'll be moving towards qubit, right? Like I showed you a basically graph, basically quantum gates, matrix, and these things. So I basically personally made one, right? This one. Basically, we knew the concept that in case of zero, we get one and zero, right, in the matrix form. And in case of one, we get zero and one. Basically, this is a standard for the qubit, right? So you can memorize it, or you can, just place it in your memory that this is it, what it is, right? So if we combine both, we will get a one. We will get a two cross two matrix identity, right? Okay. This is for single qubit. But what if I have two qubits, right? So in case of 0, 0, we get 1, 0. If we combine 0 two times, then we'll be getting this, right? As I have given you the basic concept in this. If I make it two times, right, then I'll be getting this. Till last, I'll be getting 0, 1. If we combine two times 1, then I'll be getting this. So basically 0, 1, I'll be having 0 1 and then 0 0, 1 0 and then 0 0, 1 1 and then 0 0 1, right? And now if I have three qubits, it's a bit complex, but no, we'll try to solve it. In case of 0 0, I've got 1 and the other seven elements are being 0, right? And till the end, I'll be getting an identity matrix, right? Somehow it's not, because of some calculations and stuff, it's not a basically a identity matrix, but it basically don't follow some rules for it because of some calculations in it. uh, well, we have 0 1, and then when we have a tensor product, right, we'll be getting these values. Tensor product is basically, I'll be making another video in depth for the tensor product, but by doing tensor product of 3 cross 3, right, 3 elements, I'll be getting this matrix. In case of 2 cross 2, if I did tensor product for this, I'll be getting this matrix. These values, tensor product gives me this, right? I have 4 elements in 2 case, and I have, you know, 1, 2, 3, 4, 5, 6, 7, 8 elements in this case, because 2 की power 3 is 8. So 8 possible combinations. Okay, so what is case of swap? What is this gate? Okay, this is a swap gate basically, right? Swap gate. In case of three qubits, we have some. I guess you guys have a concept of truth tables, right? So this is same truth table. We're creating truth tables in classical for and or not, but in case of quantum, we create qubits of three tensor product of two of one, and of course swap gates, and there are many other gates too. Okay, so the main idea to keep in mind here is that if we have same state, we have no change, right? In case of 0 0 0 0, we have no change in the output. In case of 1 1 1, we have no change. But if different state, then if we have different state, then they switch state, right? If we make a truth table for understanding, here it goes. For example, if you have 0 0 1, and we need to, if you have uh, three bits, right? So we'll be making two standard in this case and leaving one as it is. So I took last two elements as standard, and in this case, zero will be flipping its state from 0 to 1, and 1 will be flipping its state from 1 to 0, so it's 0 1. In case of 1 0, 0 will 1 will be flipped to 0, and 0 will be flipped to 1, and vice versa in every other case too. But for the same states like 1 1 and 0 0, we have no change, right? Let's move towards another gate. Same is the case for this: 0 0, 0 0 1, 0 1 0, and like that. If so, here's the concept. This is basically an Hadamard gate, the main gate of quantum. If we have zero change, if we have zero, no change in states, right? Zero, no change, no change. But we have to maintain a standard again. We have 3 bits, so I'll be taking last 2 bits as a standard. So if we have zero, we have no change. If I have one, I'll be changing it the next state. So it's 0 1 1. So I'll be changing the last one over here, and I have zero, so same. I have zero, so same. I have one, right? In this case, so I'll be changing it, and this is the better understanding. This is the basically calculation for Hadamard gate that we have. We combined, we took a product, and it gives us basically 4 states for two bits. 2 key power 2 is basically 4, so 4 states. So this is it.